we're looking for a reason. Seafloor spreading is the process by which the ocean lithosphere forms as magma rises to the Earth's surface and solidifies at a mid-ocean ridge. Again, go back to that idea. You have the two plates. They're moving apart. As they move apart, they will fill in here and fill that hole and harden into rock. Okay. Now, paleomagnetism is the study of the alignment of magnetic minerals in rock. Specifically, it relates to reversal of the Earth's magnetic poles, also the magnetic properties that rock acquires during formation. Okay, there's a lot in this, so you've got to bear with me here. We need to understand what's happening here. First of all, you need to understand there's something called iron filings. Iron filings are little pieces of metal that are made of iron that are magnetic. You've seen them. Have you ever seen that game where you have the bald guy and you take the little wand that's magnetic and you drag up the stuff to make his hair, his beard, and give him a mustache and all that stuff? The stuff you're dragging up, those are iron filings, and they're magnetic. Now, when they're floating in magma, liquid rock, they float and they align themselves. They're drawn to whatever magnets are around. The biggest magnet we have is the Earth. That's why a compass works. Well, those little iron filings work just like a compass. They turn and they point towards magnetic north. As that rock solidifies and cools off and hardens, those little pieces of iron are stuck in place pointing at magnetic north. Now, to give you an example of that, think of it like if you had a piece of metal attached to a toothpick and you float it in a bucket of water. And you have a big magnet on the outside, and as you turn that magnet, slide that magnet around the outside of the bucket, that toothpick is going to turn to wherever that magnet is. It's going to be drawn to it. Now, do the same thing, and as you do it, put it outside when it's 10 degrees and leave it overnight. Put the magnet over here, let the toothpick line up, then let it freeze, that water freeze. When you come out in the morning, if you take that magnet and drag it around, that toothpick is no longer going to move because it's stuck in place because it's frozen in place. The water is the same as the magma. We have water, that's magma, and as it hardens, ice is the same as a rock. So when that rock hardens and lines up in place, you have that alignment pointing to magnetic north. Now, well, let's skip ahead and we'll go back to what happens next. If you understand that part, that's the first part of it. So those lines of that iron filing lines up with the magnetic pole of the Earth. Alright, in the late 1950s, geologist Harry Hess proposed that the valley at the center of the mid-oceanic ridge was a crack, or a rift in the Earth's crust. So think of it as a volcano that runs all the way from the Netherlands, Iceland, all the way down to Antarctica. And in that crack, the sea floor is moving away, all that's filling up the ridge, that magma is filling in to fill that crack, and it hardens in the seafloor. Hess suggested that, hey, if the seafloor is moving, then the continents might also be moving. He also said that this is what Wagner was looking for. This is his idea, the mechanism that made it all work. So as the ocean floor spreads apart, magma fills the ridge, it cools and forms brand new rock. That's why we have older rock on the outside and newer rock on the inside. Same thing here, older lithosphere, newer lithosphere is just a close-up of the same slide we saw. And here's another one, showing that each step out, you get a little further away, but that they match up and it's forming at the same time. Okay, again, pause your video. Okay, and we're back. The seafloor forms as magma rises to fill the rift that forms and the ocean floor moves away from the mid-oceanic ridge. Now, going back to paleomagnetism, remember we talked about those iron filings that line up. There's one more part of it that we haven't talked about, and that's the fact that as those iron filings align with the magnetic pole, they harden into place and they stay there. They're stuck there permanently. But the Earth itself has something weird happen. Every, I forget the time frame, a couple 100,000 years, the magnetic poles of the Earth, so the North Pole and the South Pole, swap places. When the North Pole is up here at the north side, it's called normal polarity. When it's at the South Pole, it's reverse polarity. Now, these specific time periods, it happens over history, and we've seen it happen time after time. And as it does, something weird happens. All those iron filings I was talking about, the new ones that are being formed, turn around and point the opposite way. Because they point the opposite way, and we can see that. And then they solidify this way. So, because of that reversal of the Earth, we see the change in those iron filings throughout the different years of our Earth's history. When we place those periods in normal polarity and reverse polarity in order by time, they discovered a pattern of alternating normal and reverse polarity. So it went normal, reverse, normal, reverse, normal, reverse. Makes sense. We call this the geomagnetic reversal timescale. Yes, you will need to know that word. We also found out that if we laid those out and then put stripes in the ocean floor, that we can see that each side is an exact mirror opposite of the other. So we have two here, two here, two here, two here, two here, and they line up all the way across the ocean floor. As we lay those on a map, they also match up with the geomagnetic reversal timescale. So they match right up. We're going to be doing a lab that shows this paleomagnetism, and it makes a lot more sense on, but you get the idea, I hope, as I'm going through it. So if you look at this picture, so the plates are moving this way, as they move apart. You have areas of normal polarity, areas of reverse polarity. And if you go take your fingers and touch both sides of that crack all the way out, you're going to find they line up exactly. You have the two that are real close together, they're spread apart, but it's like looking in a mirror from one side to the other. It's symmetrical, if you remember your map. Again, pause, answer the question, and then come back. And we're back. Okay, you see symmetrical magnetic patterns in seafloor rock show that rocks formed at one place at the ridge. So this is evidence that it formed at the ridge and broke apart and moved to the center. Now, the important thing about this paleomagnetism that you need to realize, this is evidence of seafloor spreading. This is the actual evidence we're going to use to talk about seafloor spreading. Okay? Got to have this evidence to back it up. Without the evidence, this is a worthless theory also, much like Wagner's was. Speaking of Wagner, because these patterns on the seafloor could also be found on land, we found out that this is a very common occurrence, and it also matches the geomagnetic reversal timescale. Both patterns appeared in rocks of the same ages on both land and sea. They agreed that this magnetic pattern showed change over time. So this showed that this seafloor had to be moving. The idea of the seafloor spreading provides a way for the continents to move on the Earth's surface. If the seafloor is red, it's like setting your pencil down on your paper. You slide your paper, pencil's going to go with it. And as the seafloor moves, the continents that are attached to them are going to move also. This is the mechanism Wagner was looking for. And I hope that we'll get the video here for you. If not, I will show it in class. Alright? Thank you. I hope you enjoyed this.